There won't be much math in this video, as our focus will be on explaining notation and clarifying some misconceptions. Many students conflate the definition of a function with the relationship between two variables. For example, they feel that the input of a function should be called x and that the output of a function should be called y. This generally isn't true though, and I'm going to do my best to explain what's going on here before diving into Leibniz notation. To illustrate this point, let's start by writing out some functions. There's nothing special about these. I am totally just making them up as I go. Now, I will elaborate more on these later, but notice that outside of the function name itself, there's only one variable in each function, x, t, and z respectively. All right, there are no y's to be seen. On the flip side, let's write out some of the variable relationships. For example, we might have the equation of a circle, or this random mess of three variables that I'm just making up, or something more explicit in the form of a y equals statement. Okay, so let's look at the functions here. When I write down a function like f of x equals x squared, the x here is entirely a dummy variable. X is commonly used, but of course it's not essential. I could have used a t, or even something like a happy face. All of these are exactly the same function. We have to give the input a name so we can see how the function is evaluated, but the name could be anything, right? It's not important. If our input is x, then on the other side of the equation we have the output. This tells us how to evaluate the function, but we haven't given it a name other than to say it is the output of the function. Variable relationships are a completely different thing. For example, in the equation of a circle, both x and y have meanings. I haven't written those out explicitly here, but we usually take them to be the coordinates of the points of the circle. And once they're defined, these are not dummy variables and hence are not allowed to be changed. Now, we often mix these things together. We might use a function to describe the relationship between two variables. For example, if f is a function, we can write y equals f of x to say that x and y are two defined variables related to each other through the function f. However, this is not the definition of f, okay? And I want you to keep that in mind. So with all of this said, now let's focus on this case where, yes, we do know that y is a function of x. And if f is differentiable, the question is, what does f prime tell us about the relationship between x and y? The derivative is the instantaneous rate of change of y with respect to x. If we want to indicate this value without having to refer to the function f, we write dy divided by dx. And while it won't come up for us too often, the units of dy dx are the units of y divided by the units of x. So as an example, let's suppose that I tell you that position k is given as a function of time t. Then dk dt is the instantaneous rate of change of position with respect to time. Right? That's something that we also commonly call velocity. Here you can see how position and time appear in our description. Now we could change this example up a bit by saying let g be the amount of fuel that we burn, in which case dk dg is now the instantaneous rate of change of position with respect to the amount of fuel burned. Conveniently, we didn't have to redefine the relationship between k and g. We were able to use this notation, called Leibniz notation, to go directly to the change of k in g. As a different example, let's suppose that you're told that the demand D of a commodity is a function of its price P. Then dd dP is the instantaneous rate of change of demand with respect to its price. In economic circles, this is the marginal demand of price, or often just called the marginal demand. So Leibniz notation allows us to discuss the rate of change of one variable with respect to another which we can in turn relate to the derivative as long as those two variables are related to each other through a function.